in that group. Whoa. Sorry about Monday. That was the weirdest thing.
Hello.
I outage been right in the middle of my classes. Could have happened any other time. But anyway, sorry about that. And thanks for coming back. And I promise I won't that as I was doing when we left. I think that was causing people physical pain. And all I was doing was trying to demonstrate how many different groups of 4 we can make out of people, which obviously there is an answer to that. And I know just from knowing the formulas, the answer is 15, but it's very cumbersome to figure them all out. So I guess there's a lesson in that. But we don't actually have to figure them out to do that. That was a little too, they got to be a little too much for these old eyes. But we'll look at the formula today, because with a lot of things in statistics, we don't really have to know what each one of those little subgroups looks like. We just need to know how many. So we're going to see a formula today that lets us find out how many and how we know that there's 15. And we can actually do it with a smaller group, but I don't even want to go down that rabbit trail again after last class. So let me show you again what we were going to do on Monday, but that we didn't. And this is all in a lead up to the binomial probability distribution, which has a formula for that, for calculating probability. And it contains this. So you kind of need this as background for that. But like I said, in the end, we're going to just use an online calculator for the whole thing. So if it starts to look pretty ugly, just hang in there. Don't worry. We're not going to do all the tedious work ourselves. We're going to use technology to help us with that. So I think we were talking about combinations. And the question we were going to answer was how many combinations of 4 students. I took 6 students out of this class, 6 names, and I wanted to know out of those 6, how many unique groups of 4 could I find? And you know, it turns out oftentimes being way more than you think it is. But they add up pretty quickly. All right, so combination, the question was, how many unique, and when I say unique, I mean the unique 4 people. They could be in any order. Now, when order matters, there's different formulas, but we don't really need that, so we're not going to bother with that. How many unique groups of 4 can we make out of a group of 6? And this applies to anything. Of course, when the numbers get bigger, you get more combinations. Doing it by hand would get even worse. Now, you need a little bit of notation before we can do the formula. Did any of you in any of your previous math classes learn about what a factorial is? Does that sound familiar?
I don't think I have, but maybe I forgot.
I don't think so.
What was that?
I've heard of it. I just don't remember what it means.
Okay, yeah, I mean, who remembers these things one semester to the next? But at least you have heard of it. What it is, it's just a shorthand notation. It's not any kind of new difficult formula. It's in a class like this, when you're talking about probability, you often end up with a series of multiplications, like 10 times 9 times 8 times 7 times 6. And it happens a lot. And you really get tired of rewriting that. 8 times 7 times 6 times 5 times 4. So the notation looks like this. It's an exclamation point. And if I write 6 with an exclamation point after it, what I mean is this. So this may look familiar. It's this number, whatever that happens to be, multiplied times every whole number less than it, down to 1, of course, because if you used 0, it would cancel everything out. Now, some people leave the 1 off also, because multiplying by 1 doesn't do anything. So it's just shorthand. So when you see 6 with an exclamation point, it means all this, because we get tired of writing all that pretty quickly. And you can imagine if it was 38 factorial, you wouldn't want to have to write that out, 38 times 37 times 36, all the way down. So it's just shorthand notation. That's all it means. And it appears in this formula multiple times. And the formula for these combinations and I'll do it with the numbers we have up there first, but it works in general. If I want, and the combination formula, we do this for you got shorthand for everything, don't we? It's a big C. And on the left subscript of the C is the larger group. I had 6 students, and on the right subscript is how many I'm putting in each group. So that's read the combination of 6 items taken 4 at a time. So the overall group is 6, and we're grouping them into groups of 4. So that's what that is. And the formula for calculating that looks like this. 6 factorial divided by 4 factorial, and then 6 minus 4 factorial. So worked out, that is 6 factorial over 4 factorial. And 6 minus 4 is 2, and 2 factorial. So we could write out all these multiplications. They're not too long. 6 times 5 times 4 times 3 times 2 times 1. That's our numerator. On the bottom, 4 factorial is 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. So what I've written up on the top here, this is the expansion of 6 factorial. And down here, that is 4 factorial. And this part is the 2 factorial. So do you see how that formula works?
Yes.
Yeah. Messy, but just really when it comes down to it, multiplication. And the nice thing, since it's all multiplication on the top, and it's all multiplication on the bottom, I can start canceling things before I even multiply. For example, let's see, 3 times 2 is 6, like that. 4 cancels with 4. 2 cancels with 2. Now I'm just left with 1s on the bottom. So what do I have left on the top? 5 times 3 times 1, and on the bottom, 1 times 1. So I got 15 over 1. So there are 15 groups of 4 I can make out of that group of 6. Sounds like quite a lot. Let's see. All right. Now, in general, the formula looks like this. In general, meaning for not for specific numbers, but just for any two numbers. You would say the combination of the big group that has n items in it, and we're taking them x at a time, would be this number goes in the numerator. So it would be whatever n is, factorial. So this looks just like this, but with numbers, with letters in general, not a specific example. And this is x factorial n minus x factorial. So that's the formula for a combination in general. And let me just show you where that is on the calculator, because maybe you don't even want to do that. So if you're just trying to figure out a combination and you're like, I don't want to do all that multiplication, then you can go to our trusty little calculator here. Sorry, here's a bunch of other stuff for another class. And the button is under functions, or the combination formula. And I think they stick it all the way at the bottom under number theory. And it lives right down here. So there's our formula. Now the way you enter it is a little unusual. You click that first, then for that problem we were doing, then you put your 6 and then comma 4. And that'll tell you how many groups of 4 you can get out of a group of 6, 15. Really comes in handy when you're doing something larger. You know, how many groups of 7, functions. Suppose I had 35 people in class and I wanted to put them in groups of 7. How many of those could I get? Just over 6 million. You know, so how would you like to write all those out? And it's hard to believe. I mean, these numbers get huge fast. That there are actually in a class of 35. I say, I want to know in this class of 35, how many unique groups of 7 can I form? And it's actually over 6 million groups.
The first time I learned this, I don't even remember having the option to put this in a calculator.
Yeah.
I'm so mad. Like once you went to the calculator, I was like, wait, so I could have done this the whole time. Because I feel like this was in like quantitative reasoning or something like that. I don't remember.
Probably is in that class. Yeah.
That's
torture,
awful.
isn't it?
Oh, that's so awful. Thank you.
I like to show you by hand, but then I like to do the formula right away before you get really mad. Because there's no need to drag you
maybe
through.
I missed the option of doing this in a calculator, but I had no clue.
That's a math teacher thing.
Yeah.
For some reason they like to make you suffer a little bit, but
very much so.
Yeah. But you didn't have to suffer too long today. It's just, but I like you to see it by hand to appreciate what it's doing, how quickly these pile up. And had I been able to figure out those 15 groups on Monday, I think it would have been a little better, but you were there. I just remember somebody back in the background going, "Oh my gosh!" I gave their voice, and I knew
it was me.
I was torturing you a little I'm like, okay, I've gone a little too far here. I'm causing physical pain. So anyway, that's the calculator version of this. Thank goodness. And even if you use the formula, it's faster than writing all the different groups out, but it's still a lot of cancellation and a lot of arithmetic. And there's just no good reason to go through all that. We have technology to do these little tedious things for us. So we should use it. So back to my original point. And yes, I did have a point to all this. And that is back to this. And let me just make sure I get the variable definitions right here. Okay. Clear my screen. Here is the formula. And here's the big lead up to the formula. The probability Bill, boy, struggling there. Take extra syllables. Probability. There we go, Brenton. Of exactly X successes on N trials, So we're going to try an experiment. Binomial, remember, binomial experiments only have two options. That's why I say binomial. It's either yes, no, true, false. So it's either a success or a failure. So X successes on N trials is this formula, and it's going to look terrible, but we'll talk about each piece of it. Then we'll also do an online calculator for this. So don't worry about having to do a bunch of these by hand either. Here's where that little combination comes in. I showed you the combination thing just for this because it happens to be embedded in this formula. P to the X power Q to the N minus X. Now I'll tell you what all these letters stand for. P is probability of success. And then I'll do a quick little easy example so you see probability. On a single trial. And the Q is probability of failure. Now that one's really easy to figure out. Since this only has two outcomes, there's only two outcomes to an experiment. And I say the probability of success is 75%. Then what would the probability of failure be? There's only two. I know somebody's thinking the answer right now. I can feel it. They just don't want to say it. If I say you have a 75% of succeeding, what percent chance do you have of failing?
25.
There you go. So that's what it makes it very easy to calculate Q, because all you have to do is subtract P from 1. If the probability of success is 53%, then the probability of failure is the other 47%. So anyway, Q is Q probability of failure. On a single trial. And X, well, N is the total number of trials. And X is the number of successes we're looking for. And I'll show you an example and it'll become a little clearer. X is the number of successes in trials. So you hear this a lot in medical. If any of you work in a healthcare setting, you hear this a lot. For some certain procedures, they give you success rates. They'll say for a cardiac bypass, the probability of a successful bypass is 90%, something like that, to give you an idea how reliable the procedure is. So if, for example, so if so through years and years of data, the probability of success has been determined to be I'll just use the abbreviation here, cardiac artery bypass graph. They call it cabbage a lot. So if the probability of success got ahead of myself a little bit, is 9%, or we also know that that's 0.9. Then if a surgeon does 8 of these graphs in a day, what is the probability of exactly seven successes. So you're a surgeon. You've got 8 bypasses on the schedule today. I don't know how many they do in a day. Before you perform any of them, we know that normally it's 90% success. We want to know what's the probability of having 7 out of 8 successes. Now we are saying, we had to think about what we mean in terms of the math. We are saying exactly 7. We're not saying 7 or more. We're not saying 7 or 8 successes. We can do that problem, but that's not what we're asking here. We're saying exactly 7 successes, which means not 0, not 1, not 2, not 3, not 4, not 5, not 6, and not 8. Exactly 7. So we'll plug that. I need to make myself a little room up here. We'll plug that in our formula. And a lot of times what we write, just so we remember the numbers, is this 8 trials, 7 successes. So my N is 8. That's the number of trials. And I'm looking for, what are the probabilities for my day? What's my day going to look like? Am I going to get it? What's the chances of me getting exactly 7 successes? That's my X. So I plug it in this formula right here. And I get combination of 8 bypass graphs, taking 7 at a time. Because when you think, I've got 8 on my schedule, when we talk about 7 successes, there's a lot of different ways to get 7 people out of a group of 8. That's why that combination's in there. First thing you got to answer is, well, how many different ways can I get 7 out of 8? It's not just 7. We saw from that problem that I did 4 out of 6 that there were 15 different groups of 4. So we have to account for all those. So that's where that gets worked in. Now, times the probability of success we were given down here somewhere, 90%. And it's raised to some exponent. What's the exponent on the P? X. So that's the 7th power. See the X here? That's the exponent for the probability. And that appears right there. Times. Now, if my probability of success is 90%, what's my probability of failure?
10%.
There you go. And the exponent there is n minus x. Well, that's 8 minus 7 here and here, which is 1. Now I'm going to resort to my calculator. That's enough handwork for me. Okay, I had probability of, let's see, combination 8, 7. That counts out how many groups of 8 we have. And then the probability of success was 0.90 or just 0.9 raised to the 7th power times 0.10. And that's just raised to the 1st power, which I don't really have to put in there. So there you go. You have a 38% chance of getting exactly 7 successes. We say that sounds pretty bad. But know that that's exactly 7. If you got 8 successes out of 8, that would be a really great outcome too. But we're not counting those. We're counting exactly 7. You say, well, that's kind of stupid. It really should be 7 or more. Because I would be even happier if I had 8 successes out of 8 instead of just 7. Well, that's where these get real tedious. you can see for an exactly problem like this, exactly 7, that we could do it on a calculator pretty quickly. And it doesn't need a whole separate thing, calculator for on its own. But the problem is, suppose I said, and problem, what I mean by problem, as far as the amount of work goes, if I said, what's the probability if I had 8 bypasses, 8 cabbage grafts? And what's the probability that I got 6 or more successful? What is 6 or more? What does that include? 6 or more. That includes 6 is 6 or more, right?
Yeah,
And what else?
7
Uh-huh.
and then 8. And does it
Yeah.
continue?
Well, only up to this number because we're
Okay,
only
that's
doing 8.
okay.
So
That's okay.
yeah, you're correct. 6, 7, and 8. So I would be doing this formula 3 times and adding them all together. So that triples the work. You know, if I said 6 or fewer, then I have to do the formula for 6, 5, 4, 3, 2, 1, and 0. So I would have to repeat that whole process for 7 times. So you can see where it gets very unappealing to do. And that's when you have to accumulate. And when we talk, that's usually what we mean. When we say you're a cardiac surgeon, and so we're evaluating you. When I say 7 successes, what I really like to see is 7 or more. 7 successes we consider a good outcome. And of course, then if we consider 7 a good outcome, 8 would be even better. I'd want to include that. So more times than not, you're talking about these accumulated probabilities, which means multiple, doing it multiple times. So that's where the other calculator comes in that I'm going to show you today. It calculates what would take, it could take an hour of hand arithmetic to figure these things out. And nobody wants to do that anymore. That's for the olden days. I definitely don't want to do it anymore. So the challenge becomes, since we're going to use an online calculator, is interpreting this. Unfortunately, we did it in a previous module not that long ago. What that means, 6 or more, 6 or fewer. And we talked about that in a previous module not too long ago. When we say 6 or more, and we have a group out of 8, that means 6 and 8. So that really becomes the biggest challenge, is interpreting the grammar that we use here in the word problem and turning it into the proper math. So all this talk to get me to that point. Let's look at that calculator. Then we're going to go back to the practice problems and we're going to do a bunch. And we can knock them out pretty fast. And like I said, as long as you can turn the words, the grammar part, into the proper math terms, they become pretty easy. Famous last words, right? No, it's easy. It's easy. So let's see here. I got to look up my calculator. No, I don't want the binomial probability formula. I got so many toolbars up here. Calculator. I want a certain one because this one right here is the one I prefer. And it's nice if we all use the same one. But you can, if you want to go out on your own, you certainly can. But I use this one that's by StatTrek. I guess it's a play on Star Trek. StatTrek.com. If you Google binomial probability calculator, that's what you'll get. And I think there might even be a link on Canvas. Let me see if I was smart enough to do that. I'm not always smart enough. You guys know that by now.
You're pretty smart.
Well, thank you.
Made it this far.
You're welcome.
Depends on who you ask. Let's see. I gotta log in my mini login codes here. Let's see. This thing syncs with our phone, and then we gotta look up this unique little numeric code that resets every 60 seconds and put that in. All right, here, Math 245. And two down here, two binomial probably. No, I didn't carry it over, so I wasn't smart enough. See, I proved you wrong. I was not smart enough to put it in here yet. I probably have it in my old one. That's my excuse. But
Hey,
anyway,
all is forgiven.
thank you. That was easy. So I will just click it here, and I'll try to remember to paste this link in that section so you have it. It looks like this. It's no big deal. We put in the top 3 boxes, and then it calculates, it gives us 5 answers. And the trick becomes choosing the right answer based on whether the problem asks exactly, more than, less than, no, fewer than, that kind of stuff. So like I said, that's the part that we'll really practice, is choosing the right one. But the one, if I was going to do the one I just did about the bypasses, we would say probability. I don't want to do that way. We had 8 bypasses. So that is our number of, number of successes. That was X. We wanted 7 successes. And, oh wait, I got to read first. Probability of success. Jeez. You guys are forgiving. 0.9. Is the probability of success. 8 trials total. So that was the total number of bypasses you were going to do that day. You had 8 on your schedule. And we wanted to say, okay, what's the probability of having 7 successful ones? And then you do have to remember to always hit the calculate button. And our question asked for exactly 7. So here it is. X is equal to 7. And there is the answer that we got by hand. You say, well, what are these other numbers? Well, this is X less than 7. So what's the probability of you getting less than 7 successes? That's 18%. What's the probability of you getting 7 or less successes? 56%. The probability of getting more than 7, 43%, and the probability of getting 7 or more, 81%. And that's what I was talking about. Normally, when we say we're measuring how good you are, and we say 7 successes, in our mind, we're thinking 7 or better. And that's what that last box gives us. That says that's the probability of getting 7 or 8 successes in a day, 81%. So there's that calculator. And now we're going to look at some problems. I keep saying that. Now I'm actually going to do it. And they might be kind of, it is. We kind of skip through this sometimes because they're not always in the right order, the order we like. Let's see, preview my quiz or my work. Okay, here's one, right? Number 1. So remember, let me write this up. N is the number of trials. because we need to identify N, X, and P. So we'll identify N in these problems. That's the total number of trials. X is the number of successes. So X is always going to be less than or equal to N. You know, if you only do 10 bypasses in a day, you can't have 12 successes. So X will be less than or equal to N. So that's number of successes. And then in our formula, P was the probability of success. Now in our formula, we also had a Q, which was the probability of failure, but the computer doesn't need us to figure that out. It can do that on its own, because all it has to do is subtract it from 1. You know, if the probability of success is 75%, then the calculator already knows that Q, or the probability of failure, is the other 25%. So we don't have to worry about that. So let's look through here and pick out these numbers. 70% of all adults over 50 wear glasses for driving. In a random sample of 10 adults over 50, what is the probability that at least 6 wear glasses? Now, these are one of the problems that these really annoy me because I do this on purpose. The fact that this 50 is an age that doesn't come into the calculation at all. It doesn't matter how old these people are, but they throw these extraneous numbers in here just to throw us off, because we're going to try to stick that 50 in a formula somewhere, and it doesn't belong. That's just talking about how old these people are. So I don't like when they do that, because I think they're being tricky, and they don't have to do that. What now? N, X, and P is what I'm looking for. What is the 70%? It says that's the probability that somebody is wearing glasses. So would that be N, X, or P?
That'd be, would it be N or would it be P?
Yeah, well, it's a
Oh,
probability. Your second answer was correct.
yeah, okay, yeah.
Yeah, it's the probability of success. So usually when we're identifying a probability, we can look for something that's a percent or a decimal. And when I say probability of success, that changes for each problem. In this particular problem, wearing glasses is a success because the problem at the end asks about how many people wear glasses. So for this particular problem, that's a success for this experiment. You know, I know it's not a success that you have to wear glasses now, but you can't think of it that way. You think the experiment that we're doing is counting the number of people that wear glasses. So when we find one that wears glasses, that's a successful outcome to our experiment. So the probability of success is our P, and that is, here it is, that's my P. And I just crossed through the age thing because that annoyed me. That doesn't happen that often, but every now and then you just throw another number in there. All right, now N is the total number of trials. That means out of all the people that wear glasses, we selected a group to test. So N is the number of people in that group we selected. So what is that for this problem?
10.
Very good. Now, if you get X and N mixed up, the calculator will let you know, because remember, X always has to be less than N. But for this problem, N is 10 because we took a sample of 10 people. That's the group we're working with. We're not working with every 50-year-old who wears glasses. Now, how many out of those 10 adults, how many successes are we looking for? We want to know how many, we want to know about a certain number that wears glasses. Like, okay, I got these 10 people. Yeah, I heard somebody say it. Who's that?
It was Mallory.
What'd you say, Mallory?
I said it was me. I said 6.
And you are correct. Now, 6 is the X here, the number of successes, the number that actually wear glasses. But we also have to keep in mind that it says at least 6. Okay, so 6 is our X, but when we get all those answers, when we put it in a calculator, we have to ask ourselves, which one of these answers is at least 6? Which one of these represents at least 6? So we'll put in this N, P, and X first, and then we'll calculate our probabilities, and then we'll look at which one represents at least 6. And when we're talking at least 6, and we got 10 people, what numbers are we talking about? 6 is at least 6, right? Then it would go up, right? 7, 8 people would be at least 6, 9 people would be at least 6, and 10 people would be at least 6. So it would include these 5 different outcomes, and so we would have to do that hand problem 5 times if we didn't use this calculator. Nobody wants to do that. So anyway, let me put it in here and see what we get. I got to get rid of this mess I've made. You guys can remember numbers for me. All right, the first one . What was the probability of success? 70%, right?
Yes.
0.7. Where's my point? There it is. 0.7, 70% chance of success. And my total number of trials. How big was the group I was working with?
10.
10, thank you. And
6.
6. Now, this calculator doesn't auto update. So you do have to hit this calculate button every time. And sometimes it carries over the answers from your last problem. So don't get tricked by those answers. Make sure you always hit calculate. And hit it again if you have to. All right. Now is it? I don't know why it's not calculating. I'm sure this has everything to do with my put it in again. But it'll work fine for you. It's just not working fine for me. 10, you said, and 6. And calculate. There we go. Oh, I'm just going to complain about all these stupid ads. All right, there it is right there. So it gives us 5 different answers. And which one to use is determined by these. This is X exactly 6, X equal to 6. And we wanted what, 6 or fewer?
I think that's what it said.
Yeah, 6 or fewer. So obviously that's not what we want. This is exactly 6. Which one is it? Instead of going, look at those remaining 4. Which one of those 6 or fewer? And this problem means 6, 5, 4, 3, 2, 1, 0. That's 6 or fewer. Which one of these represents 6 or fewer? Looking at that, is that X less than 6? Is it less than or equal to 6? Is it greater than 6? Or is it greater than or equal to 6?
Would it be the one that's under the one that you crossed out?
This one here?
Yes.
Okay, what numbers, when you say X less than 6, what numbers does that mean? What does that mean in math in this problem? Is 6 less than 6?
Oh, oops.
You're close though, Lexi. Because this one, the second one means less than 6 would be 5, 4,
Yeah.
3, 2, 1, 0. Like I said, this becomes the challenge in these problems. But the more of them we do, the better you get at it. Which one of these would represent 6 and also all the numbers less than that?
Wouldn't it be the 0.350?
Yes, it would. Very good, Mallory. Because this one includes the 6, doesn't it? Less than or equal to 6. When we say less than or equal to 6, this is what we mean. Does that make sense? This stuff is just like playing an instrument or riding a bike. The more you practice it, the better you get. So don't expect to have complete comprehension on the first problem. That's very good, Mallory. It's 6 less than or equal to 6, because when we say X is less than or equal to 6, we mean 6, 5, 4, 3, 2, 1, 0. And that's the same as 6 or fewer. So this, and I could probably make, and maybe I will, make a little chart. This means 6 or fewer, X is less than or equal to 6. Because there's only so many ways they can word these things. So maybe I'll try to do that before next class. Let me make a note. Because that is the confusing part. All right, so Mallory guaranteed us that it's 0.35. And we're going to see if that's one of the answers. What did I put in wrong? Oh, it isn't or fewer. Sorry, I forgot that it's not fewer, it's at least 6. I should have gone back and looked at it. Mallory, for the problem that I asked you, you were correct. So, but unfortunately, I asked you the wrong problem. I said 6 or fewer. This is at least 6. And when we say at least 6, sorry, everybody, I should have taken a minute and just looked back at the problem to make sure I had it right. At least 6, what does that mean?
Greater than or equal to?
Yeah, at least 6 means greater than or equal to. So which one of those, which one of it is it?
The 0.84.
Right. This means, so sorry, but Mallory, you were correct for what I asked. But
That's
unfortunately,
okay.
I asked the wrong question. So it's X greater than or equal to 6. That's 6. How do they work? See, I forgot already. How do they word that? 6 or more?
At least is
Oh,
what
at
they
least.
used.
At least. So that means at least 6. So 0.8497. That should be the answer. Rounded. That. Well, there you go. Me fumbling my way through the first problem. Hopefully better luck on the next one. Now that's the problem we already did. All right, here's another one. Now, here again, they throw these ages in here. The ages don't mean anything. You know, they don't get plugged in a formula. They're just people's ages. And so we don't have to worry about those numbers. The probability that a woman between certain ages was never married is 40%, 25 and 29. And that number moves around a lot. It used to be years ago, people were, men and women were very young when they got married. Then it trended older for quite a while. And now it's really trended younger again. I notice people are quite a bit younger when they get married. I see early 20s, and I'm glad that you all are that mature. I could have never been married when I was 23 years old. That would have been a mistake. I was still acting like a stupid kid. So, but I noticed a lot of my students, you know, they just get done with college and they get married, and it feels young to me, but that seems to be the trend. But anyway, the probability of being never married is 40%. If a random survey of 10 women in this age group is taken, so we take 10 as a sample, what's the probability that 2 or fewer were never married? So I'm going to write my numbers over here. So I hopefully don't make the mistake I made last time. I need to identify my N and my X. And when I write my X down, I'm going to write whether it says fewer, more, exactly, and then I'm going to write my P down. All right, what is my N? What is the group I took that I was going to study? I surveyed how many people?
10.
There we go. So that is that group. My X, how many successes was I looking for?
2 or fewer.
There we go. And I'm going to write or fewer here. Trying real hard not to repeat my mistakes. And then what's the probability of success? What's the probability of never being married? In this
40.
problem, that's considered a success. Yeah, that's considered a success in this problem. So 40% chance that a woman in that age group was never married. So that's our probability of success for this problem. Well, that should be everything we need. Let's go do our math. And all those flashing ads over top of my numbers. That doesn't help anything. So let's see. The probability of success was, you told me 40% or 0.4. How many trials did I have? It was 10, wasn't it?
Yes.
N is 10, so I don't have to change that. And then P is
2.
2. Now, look, when I put that 2 in there, okay, you see it. Just remember, even if it leaves those, I know sometimes it leaves numbers in those gray boxes, and just make sure you hit calculate again. I don't know why this is being so difficult calculating. It's not going to do this to you. It's just picking on me right now. It's going to make me refresh every time. Well, that'll be annoying.
I'm sorry, I didn't hear you when you at first started putting it in. Was that A supposed to be there or no?
The what?
The A, I think that's what it was.
An
I
A.
couldn't hear you. I didn't know if you like had messed up or if that was supposed to be there.
I don't know. Yeah, I'm not sure where the A would have come from.
It was in the first box. So maybe it was an accident. Okay.
Probably was a typo.
Okay, because I couldn't hear you and I didn't know if
Okay.
that's what you were talking about.
Sorry.
Sorry.
That's probably me fumbling around. Most likely.
It's okay.
It's 10 trials. Too big. I'm gonna tell you what, this thing picked a good time to go wacky on me. How in the world was 10?
Oh, wait. No, wouldn't that be 0.40?
Yeah, I'm sorry.
Okay.
I am losing it. There we go, 0.4. That's why it was too big. Probability can't be 10, can it? No, now number of trials, that's the 10, isn't it?
Yeah.
And the number of successes was 2 or fewer. So that's the 2. And now it should magically work. There we go. So there are my 5 different probabilities. This one is if we're looking for exactly 2. Wait, that's exactly 2. We're looking for exactly, but that's not what we're looking for. This is if we're looking for less than 2. This is less than or equal to 2. This one is greater than 2. And this one is greater than or equal to 2. So which one, when we say 2 or fewer, if you can read it here under these ads, 2 or fewer, which one of these is 2 or fewer?
The 0.16.
That's correct. Because 2 or fewer means 2, of course, 2 or fewer, 1 and 0. And that's less than or equal to 2. So that's 0.16729. There it is right there. All right, we still have quite a few of these to do, and then we'll have the graded homework assignment, which will word the questions a little more like they are going to be on the test. And we'll do all that or start on all that Monday. We'll definitely get all the ones on this practice and maybe get started on the homework on Monday and get that finished up. But I think this is enough for today. You can look at the ones coming up if you want to in this practice, or you can just wait for Monday and we'll do them together. But thank you all for coming today, and sorry for our technical difficulties on Monday, but we should be good to go.
That's okay. Have a good day. Thank you.
Thank you.
Well, have a good weekend.
You.
You too.
Bye,
Bye.
everybody.
Bye, Mr. Bye.
Bye.